All right, guys, here we are, second part of lesson 4. This is going to be double angle, mainly identities. All right, so we've talked about the Pythagoreans, and we've proved them in the first part. Now we're going to look at these double angle, okay? And recall from last class, we did the sum and difference for sine and cosine. We proved them. And then we just kind of addressed tangent, but we didn't prove it, and that's okay. We're not going to require you to prove tangent for this class, all right? What the double angles are probably what you think, right? Well, what's the sine of 2a? What's the cosine of 2a? What's the tan of 2a? So if you have some angle and you double it, how does that affect the sine, the cosine, the tangent values, all right? We will also come up with 3 total identities for cosine 2a, because you'll see sometimes there's a better substitution, a better identity to use for that. Okay. So, well, here they are, right? The sine of 2 alpha, or 2 theta, is 2 sine theta cosine theta. You have these 3 for cosine squared, these 3 for cosine 2 theta, cosine squared minus sine squared, 2 cosine squared minus 1 minus 2 sine squared. And you have these for tangent, this one equation for tangent. Let's actually prove these, okay, using the sum difference. So I hope I have enough room. So yeah, let's go right here for sine of 2a. Okay, well, I think you guys would agree that's really the sine of a plus a, right? 2a is a plus a. So if I have that, I can just use this identity, right? A plus a, and fill in here. So that's really equal to sine a, cosine a. And it's a little bit weird because this b is actually an a, right? So wherever we see a b, here and here, we're putting in an a. And then the second part would be, well, that's plus the cosine a times sine a. Right, again, because if this is an A, that's got to be an A. So what does that turn into? Well, that's really 2 of the same thing, right? Sine A, cosine A, and cosine A, sine A, they're the same thing because they're both multiplied, and you can switch the order of multiplication. So this really just becomes 2 sine A, cosine A. All right, easy. And that is a very important one. If you guys are taking AP Calc next year, you'll use that one all the time. All right? But again, it matches what's here. Okay, we're going to do the same thing for cosine 2a. All right? So we'll say that cos 2a is equal to cos a plus a, and that's equal to cos a minus sine a. All right, again, if I've got cos a plus and then this is an a, cos a. Now here's the thing, when this is a plus, we actually use a minus, sine a. Okay, so this actually turns into cosine squared a minus sine squared a. All right? Now, that's fine, but sometimes in an equation we might want to rewrite only in terms of one trig function, right? So, if we're substituting for cos 2a, right now we have a cosine and a sine, and so sometimes that's not what we want. So one thing we could do is we could let cosine squared be, 1 minus sine squared. Okay, using a Pythagorean identity, and then that turns into 1 minus 2 sine squared a. Okay, so here's a second expression that equals cosine 2a. And do we have that here? Yeah, it's right here, right? So we have that one also. And you could probably figure out the other thing to do. Well, instead of substituting for cosine, you could substitute for sine, right? So you could say this is also equal to cosine squared A minus 1 minus cosine squared A. And that's going to turn into, because we've got minus and negative, it's going to turn into 2 cosine squared A minus 1. Okay? So this is an interesting one because it's got multiple ways that you could write it. Right? So we have one with cosine and sine together, one with just sine, and one with just cosine. And the other thing, we're not going to do it this year, guys, but when you do half angle, okay, you can replace, instead of cosine 2a, you can write it as a, and then these become a over 2, a over 2, a over 2, a over 2, and you really use these forms of cosine 2a to prove the half angle identities. All right, but we're not going to do that this year. Okay, cool. So tan, you can also do, I almost forgot about that, but you can take this expression and write tan a plus a, and so the tangent of 2 theta is 2 tan theta over 1 minus tan squared. I'm not going to spend time with that one because it's not as important. All right, so use exact values to verify the following statements. So these are showing, I don't know if you guys can see, but this is our 2a, right? This is, let me get blue here. This is really 2 times pi over 6. So we're kind of using the identity here, right? Here, here, here. And this is also 2a. And so this is just the regular a values. So let's show that they work. Sine pi over 3, that is root 3 over 2, and hopefully that's equal to 2 times the sine of pi over 6. Well, that's a half, and the cosine of pi over 6 is root 3 over 2. So these drop, and check, it works. Cosine pi over 2, well, that's 90 degrees, that's 0, right? So hopefully that equals the cosine squared of pi over 4. Well, that's root 2 over 2 is the cosine of pi over 4, and we got to square it, minus the sine of pi over 4 is also root 2 over 2. We square that. It's the same thing. Works. Okay, this one, I think we actually did earlier. Let me go up and see. 2 tan x over 1 plus 2 tan squared. I feel like we did that. Yeah, it's right here. So the way you can actually prove that is just take this, write everything in terms of sine and cosine, and you get to here, and now we know that that equals that. So I'm just going to write in here C above, right? And really for part B. So for part A, graph, both graphs should be the same. If the graphs are the same, then the two expressions are equal. And for B, see above. And so let's see if I can remember what page that was. It looks like it was page 4. Yeah, page 4. Okay, a couple more pages of examples, and we're done. So I'm actually going to stop, make one more video for just these 2 pages. Pages, what is that, 9 and 10, or 9 through 11. And that will be it. So, hope this part was